All right, we're going to take a look at 133 M511 outline, particularly starting at number 7. And in the last class, we had taken a look at essentially, hydrocarbon refrigerants and different compositions of refrigerants and the saturation temperatures, pressure temperature relationships of various refrigerants. So now we're going to use some of that information and we're going to go into the expendable, basically the type of operation of a refrigeration system. So specifically we'll have an expendable refrigeration system we're going to take a look at. So in the outline, there is, to kind of give you a little bit of a preface, then we're going to take a look at this, but the system that we're going to use is going to utilize refrigerant 22. And the system is going to contain a tank of refrigerant that would be inside of an insulated box. And it's going to have some liquid and some vapor. About 80-20 mix is what we're going to use. And we're going to kind of illustrate that process. And now I've got a small little PowerPoint that I'm going to pull up. This is also in your lecture materials. So specifically, this one is the number 7. 133 M515 PowerPoint 7. So we'll take a look at it from here. All right. So in an expendable refrigerant system or refrigeration system, to some extent, this is a little bit like it's a once and done type of a system. It's not typically used in common practice, but it illustrates really the operation of the systems. So what we're going to do, as I had mentioned, we're going to have a tank that's inside of a tank. So in this case, we've got an R22 tank. It's inside of that insulated box, as mentioned. There's a certain percentage of liquid and a certain percentage of vapor that's in the system. Okay, so about an 80-20 mix. So in this particular case here, when we take a look at this one, let me get my pen going here. So I'm just going to make a note on here. So that's roughly about 80% at that moment. So 80% liquid. And this would be, of course, 20% vapor. All right, now the reasoning behind that, why we're using the 80-20 mix, is there are certain systems that are going to use a percentage of, that will typically have about an 80-20 mix. That would be normal. So in this particular case, most refrigeration systems, that the parts of the systems that do the cooling typically have a percentage of, let's say 80-20, 75-25. Some of them are 70-30. It's always a mixture. It would be extremely rare to not have that. So that's kind of the part of the reason why. Okay, now, whoops. And so in this particular case, at equilibrium, we know that the saturation temperature will have 144 psi. So it's just like that last worksheet 41, we had looked at, I had given you a temperature and you had to tell me what the expected pressure would be. Well, in this case, we're giving you a temperature in this example of this tank, and I'm telling you that the pressure will be 144 psi, assuming that the refrigerant is at saturation, it's in equilibrium with the ambient. So the fact of that we've got 80 degrees here, 80 on the vapor, 80 on the liquid, is the telling part of this. So it will be very stable and have a saturation pressure of 144 psi gauge. So there is no heat transfer, simply because in this particular case, since all are equal, in this case we have no delta T, so equal temps in this particular case. Now that is not going to stay that way for very long. Okay, now let's take a look at what happens here. So now, if I were to be able to take a look at this application, and what if I were to relieve? So the first thing we're going to do is we'll vent a little bit of this outside. Now there's some things that are going to happen. So the first thing, as I'm venting this outside the box, one of the things that will likely happen is that will relieve the pressure off this vapor side of things. Now, in this case, as I open the valve and I relieve that pressure, so I'm venting into the atmosphere. Okay. Now, of course, in real life, I can't do it with this refrigerant because of some legal things that go on with this. It's illegal to vent refrigerant. So in this particular case, oops, there we go. As the pressure drops in the tank, that pressure obviously fell from 144 down to 102. Now, because of that, that changed and it basically removed the vapor from this particular application. We removed that vapor, and by doing that particular case, that meant that the liquid that was at 80 had to now start to boil off because we lowered the pressure. Now, in this case, we went down, so we went down to that 102, and as I am boiling it, what's happening is that tank is actually cooling. It's kind of, let's call it a refrigeration effect or an evaporating, the effect of evaporation. So as I take a look at this thing, we've got, that means when the pressure dropped down to 102, then that dropped the saturation temperature down to 60, and of course that meant that because the pressure here was low, the pressure here had to get lower. So, and because of that, it was warmer because of this 80 here. It's saying, oh my gosh, you know, this is, our pressure is low. We're going to kind of fizzle out. We're going to evaporate. We're going to cause some of these liquid molecules to change into vapor molecules to try to find equilibrium. Every system is really trying to find that. It's always trying to do this. Now, of course, in real life, these things happen inside the systems, and it's expected that a person just understands what it's going to do inside of those. So that's the first thing that'll happen. Now, of course, as I had mentioned, we've got 80 degrees. Now, in order to sustain this boiling that's going on, so as I had said, the tank, the vapor, and the liquid are trying to find equilibrium. Because they probably won't get there, what's going to happen is there'll be a difference in temperature. So you notice how we have 60 down here and we have 80 here. So we now, in this case, have a delta T. Now that delta T is going to allow that heat to flow directly into, as the arrows are showing, right into that liquid through the tank. So that's an important concept. Now, the fact of the matter is because this liquid that's contained within the system is boiling off, in order to continue that, it has to absorb heat to boil off. It takes BTUs to do this. So the evaporation effect, the latent heat effect, that's what's got to happen in order to do this. So that heat will constantly keep on moving towards that. And then, of course, at that point, we fully expect the box to start to cool down. Now, as this box starts to cool down, let's say now we're down from 80 down to 70, and now you'll notice that our delta T went down. Our delta T went down to a 10-degree delta T. Now, it won't boil quite as fast. So what will end up happening is, as the box cooled, we have this refrigeration effect, and eventually what will happen is this pressure will start to lower down even some more, is what will end. So the concept of this is that as the pressures decrease, our saturation temperatures decrease. The temperature drops. The box is cooling. This is the concept of, to some extent, what happens inside of every refrigeration system. As we take refrigerant in its liquid form, we cause it to evaporate. And of course, it takes heat to cause it to evaporate, which of course provides a cooling effect. And that's essentially why this happened. So that's essentially what would go on in that expendable refrigerant system. But of course, as we know, the problem with doing that is legally we can't do that. That would be against the law on there. There are certain types of refrigerants that we can do, and I'll talk about that next. So, all right, so let's go back to this outline. So in this particular outline, we've got, it says, explain the basic operation of an expendable refrigerant system. So one of the things that I'd like to give you an example of on these expendable refrigerant systems would be to give you just a couple of examples. What does it mean by expendable? So what it really means by an expendable system is it simply means that, oops, there we go. What it simply means is that it gets used up, is essentially how that's happening. So, so for example, there we go, it gets used up. Now, it's additionally, whoops, edit, there we go. So what it kind of means to some extent is it's a non-replenishing system. You can't make it back up. That's kind of the deal on those things. It's a non-replenishing system. It doesn't replenish itself. It doesn't get reused. It's a once and done type of a deal. I can give you a couple of examples of what we might deem as that. So one of them that we might do with that would be, an example would be ice. Whoops, there we go. All right, there we go. So ice would be an example where you put it in a cooler. It provides you a refrigeration effect. Of course, it's not boiling, but it does, it's kind of used up. Another example would be dry ice. Now, dry ice is probably closer to what happens in a normal refrigeration system, because what happens with dry ice is you take frozen carbon dioxide, and as that carbon dioxide is, let's say that it absorbs heat, the frozen carbon dioxide molecules will literally just vaporize, and it's kind of used up. Now, of course, dry ice is extremely cold, but that's an example of those type of a system. Both of those are examples of expendable types of refrigeration. Liquefied nitrogen is another one. There's other types. So when we look back on our system, one of the things that we notice on our system is, it said, we have a tank of refrigerant inside of an insulated box. It's an 80-20 mix. So that's what we had down in the bottom here. As at saturation, we expected, at saturation, we're at equilibrium with the ambient, everything was the same, 80, 80, and 80. Everything was the same, and we knew what that pressure was going to be, okay? Now, obviously, what we had told you in that PowerPoint, we said, well, it's illegal, the operation is illegal to vent. We can't just open a tank valve and get a refrigeration effect with these controllable or controlled refrigerants that are let's call them, they're banned to be vented. So that would be pretty much almost all of the refrigerants that we use are that way. So when I open that tank, what exactly happened? So one of the things that happened was it essentially lowered, as I had mentioned, it lowers the tank vapor pressure is what ended up happening, okay? It lowered the tank vapor pressure. Let me see if we can get that select. Whoops. There we go. Tank vapor pressure on the top of the liquid. Now, item 5, it says it allows the pressurized liquid molecules to do what? So as we saw the pressurized liquid molecules, what did they do? So those molecules, the pressurized liquid molecules, what they essentially had to do was they had to evaporate. They had to evaporate. So they either, you could say they evaporated. Some other terms that I had used were vaporization. Okay, that was one example. Another example, you could say they boiled, flash off. Those are all examples or terms that we use to describe what was going on to those particular molecules. select all. Let's move that. Whoops. Okay. All right. So what must happen? So let's look at item 6. So what must happen in order to change state? So how did we get this evaporation to go on? How did we get that to happen? What would happen? So in general, when we started looking at items and changes of state and BTUs and things like that, how did those happen? Well, the first thing that typically happens with all of those types of systems is in order to get it to change state, you have no choice but to you got to add heat. That's the only way you can get things to boil, is it requires heat to happen. Now, where is it going to get the heat from? Well, in the example, the box, where did it get the heat from initially? Once I had lowered that pressure, it got its heat from the liquid itself. And then after the liquid itself, then it got its heat from the box, which of course is the process of what kind of goes on in those applications. So where does the liquid get its heat from? Well, as I had said, I would say at first, we're getting the heat from the liquid. I would say liquid itself is essentially the way we got the heat from. So at first, that's how we end up getting. So all those little liquid molecules that are sitting in that tank, they are giving up its heat. So this right here, it's giving up its heat. So that 80 degrees is doing, that's one of the first thing that's happened. All right, now, what caused it to, support that? So as I had mentioned here, at first it got the heat from that liquid itself. All right, then the tank got colder. That would be the next thing. So the tank got colder. Whoops. Then the let's call it the ambient around the tank was the next way that we got the heat from. So the only way, and what has to happen is, as that process, in every situation, all of these things, we needed the delta T is what we needed to have. That's what we had to have. We had to have the delta T in order to make that happen. So then the next thing, item number 7. So what happens to let's say the molecules, what happens to the air around that tank? Well, I think, as we had mentioned, the heat from the liquid would be, is going to come from that liquid to sustain the boiling. But then that's going to create this temperature difference. So when we say, well, what happens to the air around the tank? The air around the tank, I'm going to just put on there, it must get colder because of the delta T. So it's going to have to cool. So we obviously have, let's call it a cooling effect, is essentially what we are going to have. All right, now, as we continue on through this, and we take a look at, well, what are some of the downfalls? What are some of the downfalls? So in this particular case here, the downfalls of that type of a system. So you might have noticed that as we provided that cooling effect in the tank, you might have noticed that the tank level was actually decreasing. So it was dropping. Now, so to some extent, where do we get that? To some extent, well, the problem, one of the downfalls of this is we're going to run out. That's one of the first things that's going to happen. We're going to run out of refrigerant. Obviously, we knew that going in because we said it was expendable. Okay? So that was the first thing. So item number 2, the second downfall of this is obviously the legal part. It is illegal to vent the refrigerant. in this case, and obviously R22, refrigerant 22 used in this particular example is one of those controlled substances that goes on in here. So that's a little bit of, to some extent, of what was going on in that particular system. So we had essentially a tank, we lowered the pressure, when we lowered the pressure, the saturation temperature changed. That caused some of those molecules, because it was starting to vaporize because of the low pressure, we were able to then cause a drop in pressure, which caused a drop in temperature, which ended up causing a delta T, which of course caused a cooling effect. That's essentially what's got to happen in every refrigeration system, and certainly one that is expendable. All right, now let's take a look at item 8. All right, now we have a solution. So there is a solution to the expendable refrigerant downfalls. The fact that we're going to run out of refrigerant, and all of a sudden you'll lose all your cooling. We can address those things. We can deal with that. So the first thing that we're going to take a look at is, what if we were to figure out a way to maybe, let's call it recapture to some extent on this thing. So we're going to take a look at those things, and in this particular example. Now, I'm going to start out, and this, similar to the last one, I'll utilize the PowerPoint, and then we'll come back to this, and we'll take a few notes on this thing. Okay, so let's take a look at item number 8. So this is in your lecture materials as well. All right. So we're going to take a look at this example, or this particular one. So there's only five slides here, and there we go. All right. So in the last example, as you knew, we were venting all of this refrigerant. So, and obviously you can see the level in the tank was decreasing, which of course in a real life system you can't possibly do that. So, or you are going to run out. So in this particular example, what we're going to try to do is we're going to try to maybe recapture some of this. We're going to try to recapture the vapor that we vented from the, what was inside the tank over to the outside. So all of those vapor molecules that were boiling out of here, that were heading out of here, we got to somehow figure out a way, how can we recapture these? So we're going to come up with a process of how to do that. All right, so the first thing that we're going to put in here is some sort of a, let's say we can start out with a check valve in here to make sure that nothing will go back. So this check valve is nothing more than just something to, let's call it to keep the refrigerant from going backwards. So we want to only have the refrigerant flow in one direction. So only out of this particular box to some extent into the compressor. So the flow, as the arrows are showing, is going to be in that process. All right, so that's the first thing. So the next part of the system, obviously when we're opening this up, refrigerant's moving out, we flow into the compressor. Now, one thing that is going on in here, I want you to recognize this, that there's only vapor that's going into that compressor. So that's going to be the first thing. Okay. Now, one of the things that we know, we've got our 60 there, we've got vapor molecules, we've got 60 in here. So everything is working well. We're moving into that through the check valve, into the piston, in this particular case, or into that compressor. So we're recapturing it. All right, now, as I am doing this, obviously, in this case, the vapor pressure rises, or the vapor rises to the ambient temperature. So, of course, the vapor that was taken out of the tank that provided that cooling effect, because that was essentially cooler, in this example, the warmer ambient went to that cooler refrigerant, which of course made that a little bit warmer. So when we say the vapor rises to the ambient temperature, in real life systems, when we are done inside of the boxes, it is not uncommon to see a little rise in temperature in that line because of that reason. So that's kind of one thing as well in there. Now, we're also going to take something. So I want to point this out. We have 102 degrees at the moment right now, and we have 102 psi over on this side. Okay, now, in this particular case, as I had mentioned, the vapor pressure is going to rise with the ambient. So as I take these molecules and I allow them to, let's call it, warm up, or as I create some friction or some heat, or I build that up, and so now we went from 60 to 80. Now in that particular process, that also cranked up our pressure. So the vapor pressure went and rise up. So if the same thing, you could say this about any refrigerants. For example, if I end up taking a balloon, a confined space or a tank of anything, and I warm up those vapor molecules in a confined space, one of the gas laws identifies that the pressure should rise as well. And of course, in this case, it is indeed doing that. So that's one of the gas laws. All right, now, this particular, as I continue through here, okay, so what we want to be able to do is, to some extent, how do we take this vapor and make it into a liquid? So there will be no refrigeration effect unless I can somehow take vapor or somehow put liquid back into that evaporator. So I've got to be able to do that. All right, now, in order to do this, so the refrigerant that was used in this example, we're using refrigerant 22. And as I'd mentioned, we have 80 degrees there, which correlated to the 144 psi. In the chart, they're showing 143.6. So that means that if I can somehow elevate that pressure to some extent, I could cause it to condense. And we're going to take a look at that. So if we can increase the vapor pressure and make that vapor pressure much higher, we can cause an example of, let's say, condensation. We can create that effect, and we'll describe that. We'll take a look at that. So in this example, if we increase that pressure from the 144 up to 226, let's say we crank it up to 110 degrees. Now, this is, of course, saturation. So by me bumping it up to the 226 psi, what's going to happen is that will change, the pressure is changing the saturation temperature from the 80 to the 110. So now if I put that 110 degree saturated refrigerant in an area that's colder than the 110, I'm going to get some cooling effect, or I would say that I'm going to cause that refrigerant to want to go to be a liquid to some extent, is what's going to happen. Now this is kind of, we have a part in our system that causes this to happen, and I'll describe it, I'll show you what happens. So as I had said, if you increase the pressure, and we typically use compressors to do this. We use a piston or some other process. And in this case, we're going to increase that vapor temp. And as we do that, as I had mentioned, from 80 to the 110 vapor, in this example, because we've raised the pressure up, now we've got to take a close look at that. So as I had mentioned, the cooler air, that is going to remove some of that latent energy from that vapor, and when we do that, it should indeed cause it to condense into a liquid. Now, in this example, we're going to show it as the 110 degree vapor will condense to a 110 degree liquid, is how this is going to happen. So let's take a look at how exactly that happens. So a couple of things that, when we look in this system here, we've got our tank, and you'll notice how we're kind of running out of some of the liquid in here. So we got to do something, and do something quick. So we're going to take these vapor molecules, we're going to cause them to go into this little cylinder. Of course, this is identifying a piston in this example. Okay, and of course, as I am elevating that temp from 80 degrees at 144, and I cause that increase in pressure. Remember, our check valve is in here. So that's only going to allow the refrigerant to flow one way, and only one way. So that will only allow it to go in that, as the arrow is describing. So now, as this piston goes down, I'm going to see that pressure rise up. So in the previous picture, we were looking at the pressure went up to from 110 or 144 up to 226 psi, which of course changes the saturation temp. So as you increase the pressure, you'll see the temperature increase. Now, that's the first thing we'll look at. Now, the cooler ambient, that's around here. So remember what I had told you, the 80 degrees. Now, we have a delta T, so the heat flows from hot to cold. Of course, that means my 110, in this case, the 110 degree refrigerant, saturated refrigerant temperature in that cylinder, to the 80, you know that it's going to go in that particular case. So how do we do that, or what do we do with this? So how we take advantage of that now is we've got to somehow send that back into that cylinder. So the cooler ambient, we force that refrigerant to condense from a vapor to a liquid. Now, every single refrigeration system is going to do something on this order to some extent. So let's take a look at this. So a little recap of the 226 psi liquid boils or has a saturation temperature of 110 degrees. Now what we're going to do is we're going to take that liquid that's at 110, and you're going to probably think like there's something wrong here. How can you put 110 degree liquid back into the cylinder and have it do any cooling? Wouldn't that be heating? And you're right. So we're going to do something about that. So we're going to take and force, by using a little hose, we're going to cause a restriction. And that's going to drop the pressure down. So we're going to go from the 226 psi down to the 102 psi refrigerant. So the hose is going to act to some extent like a metering device. So that is essentially the hose reduces the pressure. So we're going to take a look at that. So 102 psi liquid essentially has a saturation temperature of R22 of 60 degrees, and that's going to go back into that tank. So we need to take a look at that. So again, the molecules are moving out of this tank. They're going into the piston or going into the cylinder. We elevated the pressure. We went to the 110. We had a delta T, so we knew that the heat was flowing out. Now the key of this part is we need to somehow take a look at what's going to happen on that side of things. So we're going to use let's call it a reducing hose or a restricting device to some extent. So I'm going to make a note on this one. So this is going to act as the metering device. All right. And as we take a look at that, as I had mentioned, the small line will act as that metering device, and we're going to lower the pressure, which of course will lower the temp of the refrigerant, and that it goes back into the tank. So in this case, we are replenishing, and we're taking all that refrigerant and we're putting it right back into that tank, so we have enough liquid in here to provide a cooling effect as we get evaporation and boiling that's going on inside of that tank. And the key is understanding the pressures and exactly what that does to those refrigerants. So that's essentially how this is going to happen. All right, so let's take a look at the outline. All right, so now back to number 8. So as I had mentioned, the solution to this expendable refrigerant problem that we're going to be taking a look at, number one is we needed to recapture it. So as we recaptured that refrigerant, what we needed to do was we needed to recapture that refrigerant the refrigerant in the vapor form is the first thing that had to happen. Now, we had to pressurize it. And now, part of the process, in order to pressurize it, is in real life, we can only, let's say, pressurize, only pressurize vapors. So otherwise we would create some damage to it. So it has to be refrigerant vapor that we pressurize. So now, there was something that happened as well. So when we had taken, as I had mentioned, must be vapor, so I'm going to make a note of that, and whoops, done. All right, a little technical glitch on the iPad here. So it must have that as a vapor. That's the first thing. All right. And in this case, one of the things that happens, there is inside of that piston or inside that compressor, when we had to pressurize it, what happened was we had a process that was called heat of compression. Okay? That's one of the things that went on in there. So I got to somehow get this to be out of this mode. Done. Okay. So one of the things that went on in here is, I'm trying to get my marker to come back up here. Of course, my iPad is being stubborn here. Okay, so let's take a look at this. Oh. So one of the things that's happening to some extent is, let's try this. Maybe I can get this to function. Nope, doesn't want to do it. So one of the things that goes on, and there's a process that's called heat of compression. So this heat of compression. Now the heat of compression, as I'm describing, it only occurs with these vapors. That only happens with vapors. Whoops. Now, one of the things that goes on is when I take vapor molecules and I pressurize them, what happens is I actually, when we pressurize them, we're squeezing those little vapor molecules together. And when we squeeze those vapor molecules together, one of the things that goes on in there as I squeeze those molecules together is those vapor molecules tend to vibrate and they tend to rub against each other and they shake. And there's a tremendous amount of heat that occurs on there as a process or as a result of that. So that's one of the things that kind of happens in this. So we can only do that in this case. So when we talk about the term, heat of compression, that's one of the things that kind of happens in this case. All right. So you cannot compress a liquid, and that's one of the things that when we talk about using the term compression, I want to point that out to you. The point of compressing liquids is you would make those liquid molecules smaller. And of course, liquid molecules cannot be compressed. They will, you can pressurize them, but you can't, and we talked about that in a previous module about the use or the term hydraulics, but you cannot compress liquid. You can essentially pressurize vapors and you can make those in smaller spaces, and as you do that, you get this heat of compression. So this is essentially, this heat of compression that goes on in here, that is essentially, to some extent, I'm going to say is due, that heat of compression is really what I would say is due to molecular friction. That's what really causes that to happen. So the heat of compression is essentially caused by that process. So that's the first thing that's got to happen. Okay, so let's take a look at item number 4. So to cool it. So what do we mean by that? What happens in here? So we talk about the process of cooling it. Removing, in order to cool it, what we're trying to do is we're actually trying to remove the latent energy And so it says, cooling it, removing the latent heat does what? So to some extent, when we remove the latent energy, that caused condensation. That caused condensation to occur. And it caused condensation of the working fluid. Now the working fluid in this case was the refrigerant. So that's essentially what happened in there. So it cooled it, like, the cooling effect that when we remove the latent energy, that essentially caused that condensation to occur into there. Then item number 5, we said, well, it sent it back, we sent it back into the original tank. So once we got it into its liquid form, then we said, okay, now that we have it in a liquid, we need to somehow force those molecules, those liquid molecules, to, let's call it, to go back into the tank so they can now boil. And of course, when you boil things, that means it took heat. It had to pull heat from somewhere to cause things to boil. And to some extent, that's really what has to happen in this system. Now, when we say we're going to send it back into the original tank in its liquid form, that's all great and everything, but we've got to somehow get its pressure lower. So we're saying we're going to allow it to flow through that metering device, and we're going to allow it to flow through that meter device and then essentially lower its pressure and temp. And so I gotta make a little note on here. So there we go. All right. So to some extent, we say we send it back into the original tank in its liquid form. We allow it to flow through the metering device. We lower its pressure by going through that metering device. And ultimately, what happens when you lower the pressure, you also lower the temp. Okay, so lower the pressure, you lower the temp. Oops. Select all. There we go. I was trying to move that. There we go. All right. And of course, we'll lower its temp to a pressure or to a temperature lower than the inside air until it's all vapor again. And that process will repeat itself, over and over and over again. So, all right. So I want to do a little labeling on this particular image here. So I got to somehow get out of this mode here. Okay. All right. So a couple of things that I'm going to try to do on this thing. All right. Somewhere along the line, this has to draw here. All right. So let's try this. I'm going to have to close that and reopen it. All right, so back to this particular image here. So a couple of things I want to label on here. So as I had done earlier, one of the things that I had mentioned is a couple of little things in here. We had talked about, recapturing that, allowing the refrigerant to flow out of the tank and flowing back into this piston or into the cylinder here. So this little item right in here, this represented, to some extent, this here represented the piston, which of course would be part of the compressor. Okay. Every refrigeration system that uses that, some sort of a mechanism to increase pressure may have a piston of some sort. There are other types we'll be getting into, but that's one of them. So a piston, we Also recognize that this one here, we know that that was indeed the check valve. And of course, the check valve in this particular case, in most compressors, they don't really have, it's a type of a check valve, but most of the compressors, they utilize a valve that's actually like a reed valve, and it's like a little small flexible plate that can bend and allow the refrigerant flow in but not out. And the reed valve this is of course inside the compressor. All right, so that's a couple of little things. This particular line, as we had mentioned here, that is the metering device. And this little metering device, it has one big fancy job, and that job is to lower the pressure and the temperature of the refrigerant that enters that tank. So what I'm describing to you is exactly what goes on in every single one of our refrigeration systems at the college, in the school, out in the workforce. It's the same thing that's got to happen. All right. The other part of the system that we had described from up above is the cooling and what goes on in this particular case on here. After we pressurize it, we said, all right, we need to, how do we do this? We pressurize it. So what does this little bottom part of this thing represent? So this little 110 degree zone, let's call it right here. So that actually is what we're going to be describing as the condenser. So that is the condenser. So this 110 degrees, I'm going to just draw that as that. So that's my condenser. So one of the things that went on in here is we knew, because this is 110 and this is 80, we know that the molecules the heat is going to transfer from the warmer substance to the colder substance, which of course that caused condensation to occur because we're rejecting that energy. We were rejecting that heat to some extent. And of course, as we travel from the condenser through the metering device, you'll notice how the temperature is changing. We're lowering the pressure and lowering the pressure and lowering the pressure. And as we went from, in the metering device, we went from that 110 degrees and we made it all the way down to a 60 degree saturation, so we would have had to drop it from the 226 to the 102 psi in this metering device. So that's one of the things that went on in there. And then we go right back into this as a liquid. And so we want to be able to do that. And of course, that's one of the processes that happens. So additionally, this entire, right here, this entire zone right here, all of this is actually what we're going to call the evaporator. Now, that is the evaporator. So the evaporator's job to some extent is to absorb heat. And as you can kind of tell, the only way that you can absorb heat, or the only way you can get this evaporating effect, as we had talked about, how do you get evaporation to occur? Well, you have to somehow be able to warm something out. You have to add BTUs. You have to cause something to happen that's going to cause those molecules to change state, to go from a liquid, which is right in this area, up into a vapor. And as you can change state, as you can boil those off, you are going to get what we call a refrigeration effect. And this will occur. So the evaporator's job to some extent is to evaporate, is to boil, it's to, however you want to describe it. There's so many different ways that we could do that. So that's to some extent what has to happen. All right. So that will conclude this particular lecture moment at the time. And then what we're going to do is I'll come back and create a separate additional lecture system on by taking a look at one of our handouts, handout M531 next.